what I want to cover now is, so what we have done is we have quantized the electromagnetic field. We have shown that the total field can be considered to be a superposition of an infinite number of harmonic oscillators, independent harmonic oscillators, through a formal analogy of the Hamiltonian with the harmonic oscillator Hamiltonian. So each mode, which means a mode will be specified by the kx, ky, kz, which means the directions of propagation k vector, which defines the frequency also, because kx, ky, kz defines the frequency of the wave, and the polarization state. So if I choose a specific set of numbers nx, ny, nz, that fixes kx, ky, kz, which fixes the frequency, and I choose the polarization state. So a wave going in one particular direction with a certain frequency in free space with a certain polarization state corresponds to a mode. If you have a wave at the same frequency propagating in the same direction but with an orthogonal polarization state, that is another mode. If I have the same direction of propagation, the same frequency, the same polarization but the different frequency, that's another mode. So when you change the direction of propagation or polarization state or the frequency, you will change the mode. You have a different mode. And in free space, this is a continuum. All values of kx, ky, kz are allowed, which means all frequencies are allowed, and for every k vector direction, there are two orthogonal polarization states. We have been able to discretize the problem by restricting our discussion to a volume of a cube of side L and applying periodic boundary conditions. So that gives me a discrete but an infinite number of set of modes, and each of these modes is independent of the others. So as we wrote last time, the most general state can be written something like this: sigma n1 is equal to 0 to infinity, sigma n2 is equal to 0 to infinity, etc. Sigma n lambda is equal to 0 to infinity. Infinite number of sums, C n1, n2, n lambda multiplied by n1, n2, n3, n lambda This implies that this is the number of photons in mode 1, which means in mode 1 has an energy h cross omega 1 into n1 plus half. There are n2 photons in mode 2, which means energy in mode 2, which means, for example, this could be frequency, one frequency, there is another frequency. There are n2 photons. That means the energy of that mode is n cross omega 2 into n2 plus half. And similarly, infinite number of modes. So for one particular set of values, you have a certain constant, and each of these numbers can go from 0 to infinity. So I'll take an example and show you what is the meaning of this. So that's a huge set of states. So for example, let me look at a situation where I restrict the number of photons and the number of modes. So suppose I say that I have 2 modes and I can have up to 2 photons per mode. What will be the states that I can obtain? What will be this sum? So I'm restricting my problem now just to understand that I consider 2 modes. For example, I will say that I am propagating in a particular direction. Say kx is equal to 0, ky is equal to 0, kz is equal to some value, which means a wave propagating in the z direction, and that defines my frequency. If I define kz, the magnitude of kz, it defines my frequency, and I say I have vertical polarization or horizontal polarization. These are 2 different modes. So if plane waves propagating along z direction with vertical polarization is one mode, plane wave propagating in the z direction at the same frequency, but with horizontal polarization is another mode. So I consider these two modes, and I say that let me look at the possibilities if each of these modes can be occupied by 2 photons, which means the energy can be at the most h cross omega into 2 plus half. So the energy can be h cross omega into 0 plus half, no photon, h cross omega into 1 plus half, 1 photon in that mode, h cross omega into 2 plus half, 2 photons in that mode. So what are the combinations I will get? So the most general state will be like this. So C1, no photon in mode 1. Let me write in the same thing. No photon in mode 1, no photon in mode 2. I am not writing the others. There are only 2 modes I am considering. I am assuming that all the other modes do not have no photons in them, and so they are not. I am not writing them here. I can have no photon in mode 1, 1 photon in mode 2. Plus, I can have no photon in mode 1, 2 photons in mode 2. Plus, I can have 1 photon in mode 1, no photon in mode 2. Plus, C5, 1, 1, 1, 2. Plus, C6, 1, 1, 2, 2. Plus, C7, 2, 1, 0, 2. Plus, C8, 2, 1, 1, 2. Plus, C9, 2, 1, 2, 2. 9 possibilities. 2 photons per mode maximum. So there is a possibility of 0 photons, 1 photon or 2 photon. And there are 2 modes. So there will be 9 possibilities. So these are the only possible states in which there are 2 modes and occupied by a maximum of 2 photons. So in this situation, you see already 1, 2, 3, 4, 5, 6, 7, 8, 9 different possibilities exist. Classically, if I take 2 modes, which means a horizontal polarization and a vertical polarization, I need only 2 complex numbers, the amplitude and phase of each of those modes. There are only 2 possible. Here there are so many different possibilities. With please note, C1, C2, C3, they are all arbitrary, except for the condition that psi must be equal to 1. C1, all these are not independent. There is this condition. Normalization. So that will give you mod C1 square plus mod C2 square plus mod C3 square, etc. up to mod C9 square is equal to 1. For example, you could have a state out of this combination. I could have a state which looks like this. Let me pick up this 2 of them. So I can have a state in which I have C3 problem. Okay. I assume all the other C's are 0, only 2 C's are finite. So this is a state which corresponds to a linear combination of no photon in mode 1 and 2 photons in mode 2, or 2 photons in mode 1 and no photon in mode 2. That's one example, for instance, from this. So there are actually, it's a huge set of states that is possible. So the quantum states actually are very, very huge in number and largely unexplored still. We will look at certain types of states that people have studied and one can generate and work, and which have applications. And apart from them, there are still a large number of states which one can look at and maybe still unexplored. So the space of quantum states of the radiation field is enormous. So before we, so let us start with the simplest situation where I look at one mode of radiation, single mode radiation field. Single mode radiation state. By this I mean that my radiation is in a state in which all modes except one are empty, which means this in this state, all n values except one of them is non-zero. That means there is only one mode excited. It could be, for example, mode what I call as 3 here. So only n3 is finite, n1 is equal to 0, n2 is equal to 0, n4 is equal to 0, etc., etc. Please note, yesterday I had told you that if all the n values are 0, it's called the radiation vacuum state, complete vacuum. Vacuum in terms of absence of any excitation of the radiation states. That is, corresponding to each mode, you are at the vacuum level half h cross omega. As we proceed and discuss, things will become clearer. Okay. So, by single mode radiation field, so what I'm looking at is a situation, for example, I have a wave going in the z direction with a certain frequency and a defined polarization state. That's one mode. So, I have a vertically polarized light going in here at a certain frequency in free space. I'm looking at one mode. I'm assuming all other modes are of no concern to me or are empty, which means the corresponding horizontally polarized light at the same frequency is not there. There is no photon in that state. That is, it is in the lowest possible state. Or same vertical polarization, all other frequencies are non-existent. Or all waves going in all the kinds of directions, they're all absent. Absent, by that I mean that the corresponding n value of that mode, the excitation state of that mode, corresponds to n is equal to 0. So this would mean essentially a state in which I'm looking at n1 is equal to 0, n2 is equal to 0, some n lambda is not equal to 0, n lambda plus 1 is equal to 0. All states other than one particular state, which I call lambda here, subscript lambda, some number, or well, this can also be 0, but that is complete vacuum state. So I'm looking just at one state. So I just let me forget about all numbers and I just write this n lambda. In fact, because I'm looking at one mode, I can forget about the subscript. So I just write as n. As long as I know that I'm restricting myself to a single mode field, I don't need to put a subscript. So what it implies is I'm looking at a state, I'm looking at those states. I'm looking at those states where there is an excitation of only one mode. For example, this is an example. In general, this is not the most general state. What is the most general state? This one, with the n lambda taking on any number. All other n values are 0, which means that these sums have only one term, n1 is equal to 0, n2 is equal to 0 term only. This sum is still not summed over because you are having n lambda which can vary from 0 to infinity and all other terms are non-existent. So the most general state, single mode radiation state, will be like this, Cn n. Okay, n is equal to 0 to infinity.
So this single mode radiation doesn't have a cap on the energy that the wave should contain.
No.
It just has that only one mode should be there. It can have any energy.
Because energies are n plus half h cross omega. So it can have 0, half h cross omega to, only thing is that it can have only discrete states, but It can go to
We
infinity.
cannot have half h cross omega. That would be
Vacuum state, when there are no photons.
So is that a single mode radiation state? I mean, if
No, if I am concentrating myself only on that frequency, on that propagation direction, on that polarization state, and I find by some mechanism that the excitation corresponds to a zero ket state, it is a single mode state but with zero ket, no photons excited.
vacuum.
Yeah, corresponding to that single mode, it is the vacuum state of that single mode. Right, so that means I am looking only at one particular state, one particular mode of the radiation field, and in that mode I can have 0 photons, 1 photon, 2 photons, or a combination. That's what this is. It's like one harmonic oscillator. A single harmonic oscillator will have n ket states, and I can have a linear combination of n ket states. Because electromagnetic field, each mode is a harmonic oscillator. So this means essentially I am concentrating on one of the radiation modes, which means one of the harmonic oscillators corresponding to the radiation field. As we go through, things will become clearer and clearer. Okay. So this, when I write n ket here, it only means that right now we are only discussing single mode radiation states, which means that there is only one mode which is under consideration, and this is the most general state is you can have a linear combination of these states. So this could be this will be written in general as, which means C0 0 plus C1 1 plus C2 2 It's a linear superposition of vacuum state plus 1 photon state plus 2 photon states plus n photon state plus etc. etc. When I say a photon here, it only means that that is in that mode. I'm talking about that mode. When I say this mode is occupied by n photons, I mean it has an energy n plus half h cross omega. Later on, we will come to multimode states. But single mode states, I am looking only at one of the states of the radiation field, and I am looking at a general state of that one mode. So this is vacuum state corresponding to that mode. This is 1 photon excited state, 2 photon excited state, etc., etc. Okay, now what we would like to do is the first thing that I want to do is to look at what are called as number states of that single mode. These are also called as Fock states. That means I am assuming that only one of the coefficients is non-zero. In this expansion, only one of the coefficients is non-zero. All other coefficients are 0. And because there is only one, because n bracket is 1 normalized, so that coefficient has to be 1. Because the n ket states are normalized, and so one of the C's is non-zero, all other C's are 0. This is a special state of this radiation field. It's exactly like the harmonic oscillator being in one of the eigenstates of the Hamiltonian. This is an eigenstate of the Hamiltonian for this mode. So what it implies is a state in which in that mode there are precisely n number of photons. I'll come to this later and I'll show you that there is uncertainty in the number of photons in the state. Here I precisely know, because why do I know? Because what is the number operator? A dagger A. This is the number operator. So if I operate with the number operator on the state psi, which is A dagger A n, which I get n n. because A dagger A n is n. And this, I'm not writing any subscript. This is the creation and annihilation operators corresponding to that mode. In principle, I should write n lambda of psi is equal to A lambda dagger, A lambda, n lambda is equal to n lambda, n lambda. Okay, that subscript I'm removing because I am looking at only one mode and I don't need to put a subscript. The number of photons in the state is precisely known as n. The energy of the state is precisely known because H operating on psi is H cross omega A dagger A plus half into n, which is equal to H cross omega into n plus half into n, because A dagger A into n is n into n. This number state of a single mode number state. Please note there are multiple number of modes, infinite number of modes. Each mode can be occupied by an infinite number of sets of photons. I am picking up one mode of this infinite combinations, and in that one mode I am exciting it to a state where there are n photons precisely. Now let me tell you, to generate states like this is not very easy. Experimentally, people have generated states which are one photon states. That is, n cat there is only one photon in the state. And usually they are not single mode states, also they are multi-mode states. That means this one photon actually exists not in one mode but multiple modes. So I'll get this clarified as we proceed into a little more arguments with the states. But to generate a radiation in a single mode, single number, in a number state is not very easy. That means a state in which no other frequency is present, no other propagation direction is present, that are all in vacuum, that is, they are all in the ground state. No other polarization state is present, but except for one frequency, one propagation direction, one polarization, which is occupied by a certain number of photons. Okay, what is interesting for me to see is, suppose I had a state like this. What is the expectation value of electric field? Because that is what I can measure, for example. So I create a state like this, and I want to measure the expectation value of the electric field. Now, please remember that the expectation value of the electric field operator should resemble the classical electric field if it is a corresponding state. A classical electric field of a monochromatic wave will go as E naught sine omega t minus kz, or whatever it is, k dot r minus omega t, right? So the correspondence is, if I calculate the expectation value of the electric field of my given state, that will give me the corresponding, if that corresponds to a classical state, if the quantum state corresponds to a classical state, then the expectation value of the electric field of my quantum state must vary as E naught cos omega t minus kz or something. This correspondence has to be there. Just like in harmonic oscillator, I must satisfy the relation stating that the expectation values of the operators behave similar to the quantum to the classical equations of motion. So here, so let me calculate the expectation value of the electric field in the state. Now for this I need the electric field operator. So this recall this is h cross omega by 2 epsilon 0 v a exponential I k dot r minus omega t minus a dagger exponential minus I k dot r minus omega t. This is for one mode, which has a frequency omega, whose propagation direction is k, and actually there has to be a polarization state, which I am assuming is some given polarization, so I can look at it as a scalar and not worry about the vector. It may be horizontally polarized or vertically polarized, so whatever polarization it is. And actually I can simplify it further, assuming that the propagation direction is along z. in which case k vector is along z, and this simply can be written as h cross omega by 2 epsilon 0 v a exponential I kz minus omega t minus a dagger exponential minus I kz minus omega t. Now, the electric field is also can be written in a slightly different form in terms of what are called as quadrature operators. So, let me do that. So, let me define a chi which is omega t minus kz. I don't have to keep on writing kz minus omega t all the time. So, I just define chi, some quantity which is omega t minus kz. That is a phase. So, E cap is I times h cross omega by 2 epsilon 0 v. So, let me write. So, this is exponential minus I chi, which is cos chi minus I sin chi. Chi is omega t minus kz. So, this is exponential minus I chi. So, cos chi minus I sin chi minus a dagger into cos chi plus I sin chi, which is equal to I times square root of h cross omega by 2 epsilon 0 v into, so I will have, let me take the cos chi into a minus a dagger minus I sin chi into a plus a dagger. So, I am just expanding the exponential I chi, or exponential minus I chi and exponential I chi in terms of cosine and sine, and just coupling the terms. So, I will now define two operators which are, okay, so let me take the I inside first. So, if I take the I inside, I will get the following: square root of h cross omega by 2 epsilon 0 v into, so this I into minus I is plus 1, this I sits here. So, I will get sin chi into a plus a dagger plus I cos chi into a minus a dagger. So, I define what are called as quadrature operators. X is equal to a plus a dagger by 2 and y is equal to a minus a dagger by 2i. So, this electric field operator actually, so I divide and multiply by 2, and that 2 which I take inside the square root, so I get square root of 2 h cross omega by epsilon 0 v into x operator sin chi minus y operator cos chi. They are called quadrature operators because one of them is the coefficient of sin chi term and the other one is the coefficient of cos chi term. Sine and cosine are having a phase difference of pi by 2, they are in quadrature. Is A Hermitian operator? It's not Hermitian because A is not equal to A dagger. What about X and Y? X and Y are Hermitian operators. X dagger is equal to X because X dagger is A dagger plus A by 2 and Y dagger is A dagger minus A by minus 2i, which is A minus A dagger by 2i. So, X dagger is equal to X and Y dagger is equal to Y. These are quadrature operators and they are observables. Sorry, they are Hermitian and are observables. I can't measure anything corresponding to A cap. A is an annihilation operator, A dagger is a creation operator, but X and Y are Hermitian operators and observables. What it means is, in principle, I can measure the sine quadrature of the electric field or the cosine quadrature of the electric field. I can't measure this term or this term because these are not observables. On the other hand, I can measure X cap operator. If I measure the value of this term here, which corresponds to this term, I am measuring the sine quadrature. Otherwise, if I measure the Y cap observable, I am measuring the cosine quadrature. Yeah?
All observables or physical quantities would need to be Hermitian operators.
Yes. But all observables.
Yes. But is the other way around also, so would all Hermitian operators correspond to some...
I think so. Yeah. I think so. All Hermitian operators which have real eigenvalues should correspond to some observable.
All Hermitian operators will have real eigenvalues.
All Hermitian operators will have real eigenvalues. So some of them may be difficult to observe, maybe, but they will correspond to observables. Okay, so these are two new operators which I have defined, quadrature operators. This is like if you have a classical field like cos omega t plus phi. Okay, if I have a classical field which looks like, suppose some classical field E is equal to E0 cos omega t plus phi. So this can be written as E0 cos phi cos omega t plus minus E0 sin phi sin omega t. This is one quadrature, this is the other quadrature. So classically, either I measure E0 and phi, or I measure E0 cos phi and E0 sin phi. I get the same information. So there are techniques in engineering, electrical engineering, which use homodynamic, heterodynamic principles to measure the quadratures. And we will look at some homodynamic here later on. So this is writing the field. This is a classical expression. If you are given a function of time with some arbitrary phase, you can write this as some coefficient into cos omega t plus some coefficient into sin omega t. And cos omega t and sin omega t are pi by 2 out of phase. So measuring the coefficient of cos omega t gives me E0 cos phi, measuring the coefficient of sin omega t gives me E0 sin phi, and I can measure, then I can calculate E0 and phi classically. In fact, lock-in amplifier works on this principle. You tune the phase of the local oscillator and you can measure either of the quadrature components. I also want to see what is the commutator between x and y. So let me look at this. X, y is equal to a plus a dagger by 2, a minus a dagger by 2i. So these factors come out 1 by 4i. So this is a plus a dagger commutator with a minus a dagger, which is 1 by 4i commutator a plus minus commutator a dagger plus commutator a dagger a minus commutator a dagger a dagger. Let me use another bracket here. What is a commutator a? What is commutator a dagger a dagger? A dagger. And a dagger a, which is 1, which is minus 1. This is minus 1 and this is So this is how much? This is minus 2. So that means I by 2. They do not commute. What is the meaning of this statement? They do not commute. Which means I can't measure x, the observables x and y simultaneously. I can't measure both the quadratures of the electric field simultaneously. And there is an uncertainty relation now between the two quadratures. Okay? So, the two quadrature operators essentially give me the sine and cosine terms in my electric field, and because they satisfy a commutation relation x comma y is equal to I by 2, they do not commute and they cannot be measured simultaneously accurately, precisely. I can measure them simultaneously, but with certain uncertainties. I can't measure both of them precisely. Okay, so now let me look at the expectation value of the electric field in my number state. So this is the electric field. I can use this one or this one. Either the original expression for the electric field. I can use, let me use this because it's much simpler here. So let me use this equation in terms of chi. So the electric field is E is equal to I under root h cross omega by 2 epsilon 0 v a exponential minus I chi minus a dagger exponential I chi. So expectation value of E is for the state n E n, which is equal to, can you tell me what is the value of this? So I will have terms like, okay, so I under root h cross omega by 2 epsilon 0 v into n a n exponential minus I chi minus n a dagger n exponential I chi. I square root of h cross omega by 2 epsilon 0 v. What is a n? So I will have square root of n minus 1 minus I chi minus square root of n plus 1 n plus 1 exponential I chi, and this is 0 and this is 0. A n is square root of n minus 1, a dagger n is square root of n plus 1 ket. So does it mean electric field is 0? And how do I average this? What do you mean by average? Not time average, ensemble average. Which means I prepare a large number of identical quantum systems in exactly the same state. So I prepare a large number of n ket states. I measure the electric field at some instant of time. At one instant of time, there are so many people standing, everybody measures the electric field of the n ket state that he has. Everybody gets the value of electric field. But if you take an average, it becomes 0. This is because the phase of this field is completely undefined. The number of photons in this state is precisely defined, and there is a kind of an uncertainty between the number of photons and the phase of the field. If you know precisely the number of photons in the field, you have no idea of the phase of the field. So what is happening is, one of the observer may be finding the electric field at its maximum value, another observer finds it 0, another observer finds it at quarter of a cycle, third observer finds it negative. Please remember, they are all identical states, identically prepared states, but the phase at which, the value of phase that each person gets is different. So when you take an average of a large number of sinusoids which are not overlapped, I'll draw a figure a little later, then you get 0 electric field. Average electric field is 0.
So how can we show that there is some kind of uncertainty between the number of photons in space?
Okay, I'll come to it later. There is a problem because there is a problem in defining the phase operator itself.
Chi operator?
Not chi operator. The phase of the electric field. The electric field has a certain phase and amplitude. There is an so I have to define a phase operator, and it's not very well defined because there are some problems in defining the phase operator itself. But I will draw a picture later on, and it will become slightly clearer what is the meaning of this statement. So expectation value of E is 0 in this state. So we are looking at one nth state. Let me calculate the expectation value of E square.
So would it classically also be expect the same thing?
No?
Because the electric field varies as a cosine or sine. So if I look at
No. Classically, suppose I prepare 100 identical electromagnetic fields at frequency omega propagating in this direction z with the same polarization state. Identical, remember. Everybody will find the same electric field like this?
well, they have the same initial phase.
Yes. When one person measures 0, everybody will measure 0. 1% maximum, everybody measures the same. For all of them, it's going like this. The problem is here, the moment I have defined, because of the uncertainty principle here, defining precisely the number of photons in the state removes all, it makes the phase completely uncertain. This is not a classical electromagnetic field. Because classically, electromagnetic field should be such that if there is a quantum state which gives me a classical representation of a quantum representation of a classical field, the expectation value of electric field must vary sinusoidally with time and space. Because classically, I know the electric field goes as sine kz minus omega t or sine omega t minus kz. So, a quantum state should give me expectation value of electric field in that state must be like sine omega t minus kz. This nth state is not a state which corresponds to a classical electromagnetic field. It's a completely non-classical state. This state cannot be explained classically.
So is there any ambiguity here? Because it's a general theorem in quantum mechanics that the expectation values must satisfy the classical equations, the expectation values of the observables. So now over here it would not satisfy.
But this is not a classical state. There is no classical correspondence to this state. So quantum states are much richer than classical states. Classical states are a subset of the entire classical quantum states. So I will tell you a quantum state. I'll define a quantum state whose expectation value will go as E0 sine omega t minus kz. Yes.
But what is exactly Ehrenfest's theorem states? That it, as I think that it states that for any observable, the expectation value must satisfy the classical equations corresponding to that observable.
Yeah, but you see, I think that because quantum mechanics is richer than classical mechanics, classical states, there are states in quantum which have no classical analogs. So with what do I compare? Every classical state will have a quantum state, I think. A corresponding quantum state which will reduce to the classical state under certain conditions. Please note here that if n becomes very, very large, we are still not the classical state. Sometimes people think a large quantum number gives me, I get closer and closer to classical. No. Even if I have n a million or 10 to the power 20, expectation value of E is still 0. There are other states called coherent states whose expectation value will look like sine omega t minus kz, which will be the states which is closest to the classical state of electromagnetic fields. Okay, what I want to do is to calculate E square expectation value. So I'll have this will be minus h cross omega by 2 epsilon 0 v n a exponential minus I chi minus a dagger exponential I chi into a exponential minus I chi minus a dagger exponential I chi n. So you see, you will have a square, a dagger square, a dagger, and a dagger a. Which ones will survive? A dagger square will, a square and a dagger square will give you 0, because every time you apply the operator a, you reduce the number. So what you will be left with is the only non-zero states, the non-zero contribution will come from n minus a dagger minus a dagger a. The exponential I chi terms cancel off. A square and a dagger square will give you 0, because a times n is under root n minus 1, and once more you apply n a, you get under root n into n minus 1 into n minus 2, and because n minus 2 ket is orthogonal to n ket, you get 0. So what is this? This is equal to h cross omega by 2 epsilon 0 v into, how much is this? A dagger a on n gives me n, but a dagger, I must use the commutation relation, which is so a dagger is a dagger a plus 1. So I will get, which is equal to so expectation value of E square is not 0. So there is field. There is an electric field whose average happens to be 0, ensemble average is 0, but the expectation value of E square is not 0. And please note, even if you have no photons in the state, expectation value of E square is still finite, and the lowest, which is, so in the state n is equal to 0, the vacuum state, E square expectation value is h cross omega by. So these are called the 0-point fluctuations. Even if you have a state which has no excitation, there are electric field fluctuations in that state. Okay, we'll stop here. So I will continue with this discussion in the next class to look at the quadrature operators and look at, try to do a pictorial representation, an approximate pictorial representation to understand the result that we are getting mathematically. Any questions? Okay, thank you.